Hi, welcome to this new episode on Everyday Metallurgy. Today we're going into crash absorption, so high power impact that is taken up by metal and deformation processes. So I have invited a good friend, Carlos Moreno, to talk about it. He has been working with crash absorption for several years, and we had a pretty interesting project together a few years ago. So join us and see what Carlos can share with you.
Good.
Yeah. Hi, Carlos.
Hi, Peter.
Welcome to the podcast Everyday Metallurgy.
Hi, thanks very much.
Today we're going to talk about a very interesting theme. It's just plastic deformation, but it's not just for deformation. It's to optimize energy absorption. And you have been working a lot on that. Will you give a short presentation to yourself and where you are?
Yes, sure. Thanks very much, Peter. My name is Carlos Moreno. I'm basically an engineer. I spent parts of my life working in academia and other parts in industry. Did an HD engineering doctorate on crashworthiness. And it was mainly at the time it was trying to develop a better performance energy absorbers for the railway industry. So how to arrest the train without killing everyone on board or trying to protect the goods.
Fantastic. And today you are positioned where?
Yes, now I'm working in Warwick University as a research fellow, part of the Steels group. So my job has changed slightly from significantly to what I used to do. Now it's not as much to do with crashworthiness. Is assisting the modeling of heat treatments or processes in the steel industry, such as hot rolling processes. But still, there's similar process underlying in those processes, like you have deformation as well, you have strain. I guess they're slightly different. Now you have to deal with heat as well. Whereas when you're crushing things, heat is not much of a concern.
I was so happy that you said the name of the university, because I would have pronounced it Warwick as it is spelled. But I was told by a colleague that no, you don't say it that way.
That's true. I also, the first time I came across the name, I also said Warwick. Until I started noticing that no one else pronounced it that way. They said, "Oh, what are you saying?" And they say, it's actually said Warwick. Okay,
Warwick.
Okay. Okay, there we go.
Yeah. So now the UK listeners are also happy. But if we go a little back in time, looking at the historic background of energy absorptions, where are crash absorbers used today, and when did the industry start using it?
Yes. Energy absorbers, I guess, they are mainly used in the transportation industry. So, like cars have energy absorbers, trains have energy absorbers. I guess any road vehicle has energy absorbers because they have to comply with passive safety regulations. If you go to aerospace, that would be slightly different. For obvious reasons, planes do not have energy absorbers. I mean, it's not totally obvious, and I guess a decision was taken at some point that it would be quite unrealistic to try to prevent the death of people or loss of goods in the case of a crash because of the energies involved in a plane crash. So I don't think they include any of that, and obviously at some point someone decided that it's an impossible task, so we are not going to attempt to do anything about it. But every other vehicle, like road vehicles, rail vehicles, they are by regulation obliged or required to fit energy absorbers. So.
And then how are the crash absorbers designed? Where are they placed in the car, and how do they work? Can you describe a little about that?
Yes, sure. I mean, in the case of the automotive industry, it's a quite mature technology now, I think. So basically, the energy absorbers are incorporated into the chassis of the car. And they're basically the longitudinals at the front of the car. Is it worth showing a picture of this? Or
yes, please, please share.
Yeah, sure.
It's a lot easier to understand with a picture or a video.
Yeah. Let me show. So if you can see on the picture, then this is what I was talking about, the mature technology in the automotive industry. You see the different chassis of cars from different manufacturers. And what you can say is that they all use exactly the same design. The energy absorbers are these longitudinals that stick out at the front of the car. So you have the chassis, and there's these crash cans that are integrated into the chassis of the body of the car, and this the way these ones work is that they're crash cans, and when they are crashed along the axis of the crash can, they start buckling. But it's not a global buckling. They don't bend completely in a complete way. What they do is start buckling at small chunks. So and that's they do that naturally. So they behave basically like an accordion. They start buckling at a natural frequency, or it's not natural frequency, natural lengths of it, and it buckles a bit, and that produces a force distance response that is variable. So you get peaks and troughs from this kind of energy absorber. So when as every section is buckling, you get a peak and a trough, and then another peak and a trough, and therefore the force is variable, as well as the accelerations that the occupants are seeing while the crash is happening. Ideally, in the industry, an ideal so the forced response that I'm describing is this kind of force where you have a peak and then it peters out after that, and then you would have another lobe of the crash can, and then this would repeat itself. Ideally, from a energy absorber point of view, what you would like to see is something like this.
Yeah.
When you have a constant force all along the distance or the stroke of that energy absorber, and that force would be totally constant for that distance, and you maximize the energy that you get out of that device. So this is the holy grail of energy absorbers.
Yeah. So it doesn't exist today.
No, there's methods there's energy absorbers and mechanism that get closer to this than others. So that the one I described for automotive, the crash cans that promote progressive buckling, is that would be the word, progressive buckling, would be quite different from this ideal behavior. Other methodologies, like, so for instance, if you look at different energy absorbers, like the ones that they use in railway, These are closer to that response or the ideal response. What we are looking at is concentric tubes where you have a smaller tube inserts into the larger tube, and when you compress that device, it swells the larger tube and
just make an expansion of it.
Yeah, it's a radial expansion of that tube.
The inner tube doesn't collapse.
No, there's no collapse in this case. So the plastic deformation is just restrained to the larger tube. Obviously they use this in railway because in railway they have different requirements. So weight is not such an stringent requirement as it is in automotive. So you can build this kind of device where you have a heavy mandrel. There's no any other way to describe it. It's quite heavy, and it doesn't collapse as well. So you have this still the full length of the mandrel at the end of the crash. Whereas if you look back at the longitudinals that are fitted into the chassis of a car, those are compressing. So at the end of the crash, then they have a fraction of the original length. Whereas in this case, you are restricted to 50% of the length of the device. It's never going to collapse any further than 50%.
Then it's a hard stop.
So in railway, you can get away with this kind of devices. You can get a better forced stroke response, but obviously the trade-off is that it's going to be a much larger, less compact and heavier design at the end. Also, it will be quite more difficult to integrate this into the design or the structure of a car. So you would have to change quite a few. Or how do you connect this to the chassis? So there's work at the time. At the moment, there's people like I know researchers in Canada and the University of Waterloo who are looking at these devices now to try to adapt them for the automotive industry. So how would you connect this kind of devices to the chassis? And obviously it's a fantastic challenge, but they're looking into that.
What you have shown so far is in steel material, I guess.
Yes.
Is it only steel that is used for crash absorption, or are other materials also in use?
No, there's, I think many materials been used. Steel is obviously the cheapest one that they can get, so it's cost effective in that sense. In railways, because weight reduction is not such a stringent requirement, they tend to go for steel, just probably to reduce cost, and also because steel is such a great material. So in reality, you get a fantastic performance, and it's inexpensive compared to other materials. So what is not to like? Obviously, what is not to like is the weight. In case of railway, weight is not that important, so they can get away with that. When you go into the automotive industry, for example, it depends on the kind of range of car you're looking at. If you're looking at the utilitarian cars, then they're probably made of steel. So then the crash cans would be made of steel. But as you go higher end range of the car, then they go into aluminium chassis, in which case the crash cans are made of aluminium, or it could be composite if it's like a fancy car. In which case the ways if you, for instance, use composites, the ways that would crash, it would be slightly different. It would be it wouldn't be plastic deformation. It would be more like fracture. What it would be giving you the energy absorption, so that you basically would be pulverizing the crash can as it's being compressed. It's got also its pros and cons. as you would imagine.
Yeah.
And yeah, aluminium also is used because it's a lightweight material, but you can, from what we discussed before, that we are looking for something that can give you a great force over a long distance. So then you need something that is strong and also ductile at the same time, which aluminium probably is not as much.
So, it can be ductile for a long time. But not very strong. So if we take a deeper dive into that, because that is some of the core metallurgy in this, it's the working curve. When you make a deformation, then you have strength and elongation, and I have always understood that the energy you absorb is the area below the loading curve.
That's correct, Peter. Yeah. So the energy is the area under the force stroke diagram. So once if you put the sensors there, when you're testing one of these devices, it gives you the load cell would give you the force response, and you would have something to measure the distance, whether it's a LVDT or laser or any other device that would measure the stroke, and then from there you would just integrate that signal, and it would give you the amount of energy that you absorbed.
Yeah, I've made a previous episode on high entropy alloys, where we talked about alloys that can do that. So because when I went to school many years ago, I was told you can either have high strength or you can have high ductility, but you cannot have both.
Yeah.
But over the last 15, 20 years, new alloys has been developed up there in the middle. Not the material banana, as I called it, but up there where you have very high strength and on the same time very high elongation. Is that also something you work on?
That would be the ideal material. You can get a material that is strong and at the same time very ductile, so you can deform over a long stroke without fracturing and compromising the structure or the behavior of the device. So if you have that material, that is something fantastic. So we there's a project that we did in my previous company and with you, Peter, at Syntex, which was looking in that direction. So I don't know if you would like to introduce.
We developed the alloy system named TWIP. So twinning induced plasticity, where you could by twinning deformation, that's also known from austenitic stainless steel that make twin deformation. But by twinning, you can elongate the deformation even at pretty high strength. And these new TWIP alloys, they can go even higher. So I think today you can go up to 800 to 1000 megapascal with an elongation above 50%.
That's absurdly fantastic. Compared to the conventional steels.
And then we try to combine this TWIP material with a new design method where we make metal powder extrusion to make very complex shaped geometries. And I know you made some trials on it, and I would love if you could share how it looked.
Yeah, absolutely. Yeah.
Sorry, I'm interrupting. I just want to take a deeper dive into this the material banana. Here on the background, you can see the material banana. That is what I learned when I went to school. But today, new alloys has been developed. These we call them TWIP and TRIP. They are both very strong, as you can see here, and they have a very long elongation. So this is what Carlos really looks for when he's designing next generation crash absorber. We made another episode previously on this, where I talked to Jose Torralba from Madrid University on high entropy alloys. You can find that episode in the podcast previously. So subscribe and see if you can find it. It is very interesting to learn that you can not only make high entropy alloys, but high entropy steels that fulfill this level of energy absorption. That was the first part of this episode. In the next part that will come out soon, we'll go deeper into some of the applications and look at how we can develop this further in the future. And Carlos also have some pretty nice videos that he'll share with you. So stay tuned and wait for episode 2. You can subscribe and then you'll have it in your feed. See you.